Hi, everyone. I'm Jamie Jones, and I'm a professor in Earth System Science at Stanford. I'm actually trained as an anthropologist, but I sit in the School of Earth, Energy, and the Environment at Stanford in the Department of Earth System Science. So today, I'm going to talk to you about some recent interests I've had in applying evolutionary and ecological ideas to economics and decision theory. This interest was piqued by my attempt to understand the peculiarities of the human life cycle. And our life cycles are really peculiar, I can assure you. In a broad comparative context, they're really kind of weird. And to understand the reason people in subsistence economies pursue particular types of resources, prey and forage food and that sort of thing. And so I'm going to guide you through a big picture review of some fairly technical fields today that include population biology, decision theory, a bit of economics, both classical and behavioral. But I think the ultimate message is pretty straightforward. And the sort of broad picture that motivates me is understanding how something like this, which is an artist's reconstruction of Australopithecus afarensis, which is essentially a 1 meter tall chimpanzee-like thing that walked upright, right? It's got a 300 cubic centimeter brain, so about a quarter the size of, maybe a little less than a contemporary human. Very sexually dimorphic. The males are much bigger than females. They had enormous cheek teeth from eating a very tough diet. And as I said, they're really tiny. These guys lived about 3.5 million years ago in East Africa. And transition, and this probably doesn't look that different, I guess, but it is. It's fundamentally different in about 1.8 million years ago. And this critter, called Homo ergaster, for my purposes, is effectively modern. You've got a large body size, so within the normal range of contemporary human variation. You've got body proportions that look very much like people living in the tropics today. You've got a great reduction in sexual size dimorphism, so that males and females are similarly proportioned to how they are today relative to each other. And you've got big brains. They're smaller than modern, but they're actually within the range of variation, on the low end of variation of contemporary humans. Homo ergaster, sometimes called African Homo erectus, is the first of our family to leave Africa and to colonize the rest of the world. And it did so around 1.8 million years ago, give or take a little bit. And so my question is, how is it that a population of bipedal apes, they're not very impressive looking, right? Kind of like we aren't, right? We don't have big weapons. We don't have antlers or horns. We don't have big teeth. We don't have this sort of ferocity built into us. We have some cleverness maybe. But how is it that in less than 2 million years, which is a very rapid period of time in the broader span of evolution, how is it that we went from this small population of African apes, bipedal apes, and have grown to a size of 7 billion souls in, as I say, less than 1.8 million years? Okay, and we've colonized and come to dominate nearly every terrestrial biome. Right? Just a picture of making the desert green in the Arabian Peninsula as a sort of indicator of the extent to which we really dominate the world. 30 to 40% of net primary productivity is captured by human actions, right? So the phenomenal growth of our species in this very short period of time suggests that our ancestors on average must have made pretty good decisions, right? Because the decisions they made led them to increase in pretty great numbers. But there's a torrent of work in psychology and economics, represented by just a few sample publications here of semi-popular trade books, suggests that the decision-making software that our brains run, which is presumably essential to our ecological domination, is profoundly flawed, that in a word, we're irrational. How is it possible that a species apparently so defective in its ability to generate sound decisions can be so incredibly evolutionarily successful. I'll just say, as a relative outsider, I'll make this observation about this particular body of work that I'm discussing here in this slide. There are lots of anomalies. Like we see these things that don't make sense from the way we sort of think about the way people should make decisions. And you can write whole books on this, like lots of books on this. But they're generally unconnected, and the whole area seems to lack a sort of unifying theory. I'm going to humbly submit that I think that evolution can help us provide some of the theory that brings together some of these anomalies. There's a tendency in particular in the TED Talks where there's real selection for being provocative, right? To suggest that people are irrational because they don't follow the rules of formal or axiomatic rationality theory. However, every economic decision entails an optimization problem, and I feel like I'm on safe ground when I'm at Google talking about optimization problems, right? And if you want to solve an optimization problem, what do you need? Well, you need to know who's doing the optimizing, you need to know the actor, but you need to know the objective function, right? And if you get the objective function wrong, you're going to get the solution wrong, okay? And it doesn't matter what your optimization problem is, right? It could be an engineering problem. It could be a portfolio design, an investment portfolio design. It could be about getting the best mixture of wild foods to ensure growth and survival, right? But you need to get the objective function right. And I'm going to suggest that, in general, we don't have a very solid understanding of what the objective function is that people are using when they're making economic decisions, broadly, okay? And the results appear anomalous. When you use the wrong objective function, you get the wrong answer. And I think that evolution helps weave together theoretically what are otherwise a series of unconnected anomalies. So we lack this coherence, and I think these may be brought together if we understand what sort of problems the human brain is actually designed to solve, okay? Get the right objective function, and you have a chance. I'm not 100% convinced of this. This is fairly new for me, but I feel like there's a real chance that we can begin to understand this sort of broader theory of choice. So the two things that we really need, I think, are evolutionary theory, which guides our choice of what's being optimized. It gives us a clue as to what the likely objective function that our brains are designed to solve or to optimize. And secondly, it's really important that we get broad comparative data to help us understand the conditions that favor good decision making. It turns out that different groups of people make more or less good decisions, right? It's not everybody who's a complete idiot and behaves irrationally, okay? And we sort of limit ourselves a lot in the sort of people that we inquire about decision making. I'm going to focus primarily on the evolutionary theory and give you just some hints of some work that we've done without getting bogged down in the technical details. But I think that the comparative data is really important as well. I'm going to use this word fitness. I'm going to use it a lot. And evolutionary success is determined by fitness. And the problem with fitness is it's one of these super fraught terms, right, that has lots of colloquial meanings that can kind of interfere with our rigorous understanding and analysis of it. So when I talk about fitness, I'm talking about the relative contribution that an individual makes to future populations. So if you have some heritable trait, whether it's anatomical or physiological or behavioral, marginally increasing the representation of its bearers in future generations, the population is going to evolve towards that trait. This is the fundamental logic of selection. Right? And fitness is the evolutionary objective function. It is the subject of evolutionary optimization. Okay, so just wanted to get that out of the way. I'm going to give you a quick preview of the approach that we use in thinking about this sort of more formally. The organs that make our economic decisions, right? They're organs just like our liver is, just like our heart is. Presumably these have been under intense selection. And part of the reason, just as an aside, part of the reason we think that brains should be under intense selection is not just because they're useful, but because they're super costly, right? The brain is an incredibly costly thing to carry around. It entails mortality costs for mothers, right? Because we get this cephalopelvic disproportion. Big brains have to come through a limited pelvic cavity when they're born. Brains use 20% of oxygen at rest, right? They're super costly. The fact that they exist and that they've gotten bigger over time suggests that there's a reason they're there, right? People with good decision-making capabilities, presumably in the past, resulted in leaving more descendants and became disproportionately represented in the population. To the extent that economic decisions affect fitness, we should expect outcomes to track fitness interests more than some arbitrarily defined standard of formal rationality. Okay? So let me just walk you through a little bit of the logic here of the model, and then I'm going to move away from it and go on to talking about some features of the human evolutionary environment. So it's a hierarchical model. At the bottom, we have economic decisions, right? These are about the sort of things you hunt for, the sort of things you put in your market basket, the decisions you're making on a day-to-day basis about your livelihood, right? And these feed into what we think of as like proximate motivators. These are the things that you're sort of striving for in a proximate way. You know, happiness or sexual gratification or satiety, right? The things that motivate you to eat or to have sex or to do things that are meaningful in your life. But these then, presumably, have an impact on fitness. And we can think of as fitness here as an aggregator, something that aggregates and averages over these different, my pointer doesn't work, these different goals which are fed into by these economic decisions. Okay, so that's a preview of the type of reasoning that we're using. I'll come back to this in a little bit. But I do want to mention, you know, I said that the two things that we need, I think we need evolutionary theory. I think we also need broad comparative data on the decision-making of actual people, and particularly people who are good at making decisions under tremendous constraints. And this is just a selection of a bunch of people. They've written some books, right? And it turns out that somewhat to the surprise of much of the institution of studying economic decision-making, that poor people often make incredibly savvy decisions, right? They face enormous constraints. But when you adjust for that, when you control for the fact that their constraint set is very limited, right, that their strategy set is very limited and they're under tremendous constraint, poor people tend to make very good decisions, in part because it really matters to them, okay? And so I'm going to leave that. This is another big part of the broader work that I'm doing, but I want to focus on more the sort of evolution part. The economic decisions I'm going to talk about and show you some pictures of typically center on subsistence populations, and the things look a little exotic, but the sorts of decisions that people make in subsistence economies are fundamentally no different than the types of decisions that we make on a regular basis, right? How do you fill your market basket given a fixed budget, right? It may not be money, it may be time, it may be political capital, but you're doing very much the same sort of thing. And and basically my argument is that we have to think about humans as biological entities. We've been shaped by selection, and that our decision-making capabilities have fundamentally been shaped by this evolutionary heritage. To a biological entity, economic decisions are not arbitrary preference orderings, right? Which is sort of the way you typically will learn about them in a microeconomics class, for example. It turns out that the rules for a living organism, anchored in the present and subject to a force of selection, that really doesn't like extinction, right? Fitness is a multiplicative process, right? In order for your lineage to persist, it has to persist every generation. You can't get a zero in there or it's an absorbing boundary, right? So you really want to avoid those zeros. I'll show that the all-important need to avoid extinction in a world that's incompletely known at best has profound implications for preferences, utility, and rationality. And one of the key things I think that comes out of this is that ignoring the condition of existential uncertainty, by doing that, the theory of rational decision-making has developed a distorted expectation of how organisms working in their own interest should behave. Okay, so a bunch of the work I've done on this is in collaboration with my colleagues Rebecca and Doug Bird. And just to give you a sampling of the types of economic decisions we tend to think about. Do you hunt for goanna, which are these monitor lizards that live in the desert of Western Australia, or do you hunt for hill kangaroo? Right? There are different payoffs, there are different risks associated with this. If you're a subsistence farmer, this is in Uganda, another place where I work, do you plant maize, do you plant yams, or do you forgo subsistence crops altogether and take a stab at the cash economy? This is coffee. Working with a postdoc, Ashley Hazel, in Southern Africa and Namibia, we're asking the sort of questions: how do people, particularly women, manage social relationships to manage the extreme uncertainty of living in essentially a desert and trying to raise cattle, trying to raise crops, trying to raise children, right? Trying to keep yourself going in a very difficult environment. So these are the types of economic decisions that I tend to think about, but as I say, they're fundamentally no different than going shopping, buying a house, doing the sort of things that economists tend to look at. The history of this for me goes back to my former PhD student, Mike Price, who's now a postdoc at the Santa Fe Institute. And Mike was interested in understanding the origins of sago palm farming in Southeast Asia. Sago palm, it's an amazing crop. It's one of the centers of agricultural innovation, right, in around New Guinea, in the South Pacific, Southeast Asia. A single sago palm tree will net literally millions of calories in starchy flour, right, that you can make into a gruel that's very calorically dense. The catch is, it takes 25 years for a sago palm to develop to maturity and to the point where it can be harvested. And trying to understand the evolution of this remarkable horticultural system led us to think hard about economic topics such as time and risk preferences and economic decisions generally. It's hard to make a sort of standard economic model that says, okay, forgo the immediate reward activities you're pursuing right now and go plant some sago palm and wait 25 years, right? That's a hard problem to solve, but clearly it happened at some point. So that's where all this really started thinking, and Mike and I have been working together for a few years on this stuff. So a theme that emerged in our work is that a biological entity trying to maximize fitness will behave in ways that often really mimic the anomalies that you see in this behavioral economics and psychology literature. We weren't looking to show that, but we found how, people said, hey, that kind of looks like prospect area. I was like, really? That surprises me. So they'll do things like use non-expected utility, right? I won't get into what that necessarily means. Happy to talk about it later. They'll frequently violate the axioms of rational choice. They'll seemingly have inconsistent time preferences, right? And from the perspective of an economic decision, these may appear irrational. But these behaviors are the sort of things that keep you alive in a variable and uncertain environment. Okay? So rather than the mathematician's formal axiomatic rationality, people seem to use a procedural rationality. And this is a point that the great polymath economist Herbert Simon suggested in his scissors metaphor. Right, that trying to understand decision-making is like trying to understand the way a pair of scissors work. You've got, on the one hand, the computational capacities, but on the other hand, you've got the task environment. Trying to understand the computational capacities, like the logical rules of cognition, without understanding the environment is like trying to understand half a pair of scissors. It doesn't work very well. Okay. I said that there's selection in TED Talk-like environments for saying provocative things. This is a slightly provocative thing. Darwin's saying it. Economics isn't actually a science, right? This isn't meant as a put-down. It's a statement of fact. And it's because the preferred and overwhelmingly the dominant mode of economic theory generation is axiomatic, right? And that's not the way the natural sciences proceed. Behavioral economics and this great field of experimental developmental economics has changed this by actually measuring the way people behave rather than sort of specifying the way they're expected to behave, but I think there's still a decent amount of baggage. What do I mean when I say axiomatic? Standard economic theory generation starts from a series of axioms, right? Primitive assumptions that are taken to be self-evident. Things like you shouldn't reverse your preferences. If you prefer A to B and B to C, you should prefer A to C. That's an axiom of transitivity, right? And that makes total sense. But there's nothing that guarantees that that's right. There's nothing that guarantees that that's the way the universe works. It's just a logical rule that we say, yeah, I can live with that, right? And so you take these axioms, you derive out the way you expect a rational agent to behave. And this is what economic theory really is all about. It's normative. It describes how actors should behave. Science, on the other hand, is positive, right? It starts from observations about the world and attempts to explain them as inferred through observed data. It's inductive, right? The theory plays the role of generating hypotheses which can then be confronted with additional data, right? And so it's a common and it's a well-stated critique of that neoclassical economic theory describes the behavior of a species other than humans. And it's referred to tongue-in-cheek by the fake Latin binomial Homo economicus, right? And while it's true that humans do not behave according to the classical expectations or these neoclassical expectations, you know, the expectations weren't designed to actually explain observed behavior, right? So we shouldn't be that surprised by it, I think. So I'm going to talk to you about right now for a little bit about what I think the really important bits of our human evolutionary legacy are for understanding the way we make decisions about things. And I'm going to dive down fairly deep into my specialty area, which is called life history theory. So I'm going to suggest that humans are adapted to environmental uncertainty. And this is, I think, a pretty telling graphic. So what I've got here is it's temperature proxy data. So this is inferred temperature by a million years before present. So we're going from more ancient to more recent. Humans are a product of what's called the Pleistocene, which is a geological epoch that spans from about 1.8 million years ago to about 10,000 years ago. And the two things that should be really obvious from this plot are that, one, the Earth has cooled in the last 5 million years. It's actually cooled considerably more in the last 25 million years. It's cooled, and it's gotten more variable, okay? And you can't actually see it on here. We know that in places, particularly in Africa, where there's been a lot of interest in this, there's actually decadal scale variation here, like enormous environmental variation going on that really gets amplified in this period where our genus emerged, which is this pink line here, okay? And just while I'm on the subject of temperature, global temperature, right, you'll sometimes see people say, well, you know, the Earth used to be much warmer. We can let it get warm, it'll be fine. Maybe, sure, but we're a cold planet species, right? We are adapted to a cooler planet. Just, you know, something to bear in mind. The origin story of the human lineage and the genus Homo in particular is a story of moving from a primarily arboreal lifestyle in tropical ever moist forests. This is a chimpanzee foraging for, you can see the fruits up in the top of the picture there in the Nyungwe forest in Rwanda. We moved from these forests onto this sort of mixed scrub savanna. This is a picture from Serengeti National Park in Tanzania. And moving onto the savanna entailed a bunch of new challenges, right? There are big predators there. There are a lot of them. They're big and they're scary. But it also changes the way food is distributed. Right, and here's a picture of a chimpanzee who's in the Kibale National Park, and he's looking down at me, and he's got an enormous pile of figs here. And this tree, I don't want to exaggerate, but it certainly had tens of thousands of figs, possibly hundreds of thousands, possibly well into the hundreds of thousands of figs. These tropical figs are incredibly productive. They're asynchronous breeders, so they breed sort of throughout the year. They fruit throughout the year. They're not really high quality. Like, you wouldn't want to make a Newton out of them, right? You're not going to make figgy pudding with these because they taste like crap, I assure you. But when there's no good fruit in the forest, chimps will happily eat this. And this is in general what the great apes do. They fall back when their preferred foods aren't there onto this lower quality stuff. And figs are a great thing in any tropical forest. When you go out into the savanna, there isn't much fruit. What there are underground storage organs. So these are a bunch of Hadza tubers that my former postdoc Brian Wood took a picture of, and they look like sticks, don't they? Doesn't that look delicious, right? Try to eat that, and you're going to spend like 12 hours just chewing on it. Your jaws are going to be so tired. You have to have fire, basically, in order to, you scorch them, you burn them, and you make them chewable. There's a lot of stored starch in there, and it makes for a great fallback food. But they're very different than figs. They're widely distributed. They're not at all clumped, right? You're never going to find a patch, just start digging. Oh yeah, and you got to dig for them because they're underground. But you got to start digging. You're not going to find 100,000 tubers there, right? Like you're going to find 100,000 figs in a tree. So you have to spread out your effort, right? It changes the economics of foraging tremendously. And here's Brian, who's one of the world authorities on the Hadza hunter-gatherers in Tanzania, and his hair really is fascinating. So he gets that a lot. He's now a professor down at UCLA. So moving from the forest to the savanna and beyond increases the variability in food intake, right? Because it's a drier environment. It's a less productive environment. There are lots of opportunities, but there are also lots of challenges. And while there's certainly more sort of meat on the hoof, your ability to sort of manage your downside, I think, is much harder on the savanna. And so this is why adaptation to uncertainty is a central part of being human, right? Humans move out of the forest onto the savanna, and it's a much more variable place. And this variability is not just, you don't just like set up an experiment, measure the variability, and get your nice distribution that you fit to it and say, okay, 14% of the time I'm going to have to do this, and 27% of the time I'm going to have to do this, the way a risk manager would do it. There's real uncertainty here. You really don't know what the probabilities are, in part because the environment is very rapidly changing. So when I say uncertainty, I mean uncertainty and not risk. Adaptation to uncertainty is central to being human. There are all these things that we do that are very unusual. We have an expanded diet, as I've mentioned, that typically requires technology to extract, like these underground storage organs. We are the mobile primate, right? Our home ranges for like a hunter-gatherer is on the order of 10 to 100 times bigger than a comparable sized chimpanzee group, okay? So like the Hadza range over about 2,500 square kilometers, whereas a chimpanzee group will range over about 20. Now the chimps live in a forest, so there is that difference. But that's part of moving out onto the savanna, where the Hadza live. Humans are so mobile, right? When things get really bad, we get up and we move continents, right? This is very much a timely issue, right? The 21st century and the latter part of the 21st century is going to be dominated by human mobility, right? We see that it's breaking lots of international systems right now and possibly leading to the rise of right-wing extremism, right? Migration is part of our story from the outset. The other really big thing that we do that we're really known for and that's very unusual, right, is we share food. And it's so unusual, we don't even think about how weird it is, that a bunch of unrelated males, doesn't matter, males, females, can sit in a room and share food together and like not want to kill each other. I mean, I don't know, I don't want to speak for you, but I can sit in a room with people are eating, I don't feel like I need to go, get all dominant or something, right? This is weird, right? You talk about your dog and the unconditional love of a dog. I've got an idea. Why don't you try pulling your dog's food bowl away and eating from it? See if that love is so unconditional, right? It's a weird thing that people do. We share food all the time. And hunter-gatherers, it turns out to be a super risky and uncertain endeavor to go hunting. Those hill kangaroos, 85% of all hunting bouts end with 0 calories netted, okay? 85%. So these are mixed hunter-gatherers in the Canadian Arctic. My student Elspeth Reddy gathered these data heroically over 2 years. It's an incredible, incredible story. And it's just to show you, I mean, she also makes really pretty graphics, but it's just to show you that by having these networks of food sharing, right, you ensure against you failing on any given day. You can count on getting food from someone else. So this is also a very unusual thing that people do, right? And this is part of the argument for this embodiment of, yeah?
What do the colors mean?
So the red houses are food insecure, right? And the blue ones are food secure. It's actually, yeah. It's actually a very complicated graphic. I just show it because it's nice. So those are a few ways we manage uncertainty. But my main focus is on the evolution of our life cycles, right? How long we live, why we reproduce when we do, the patterns of reproduction, that sort of thing. And I would suggest that uncertainty is embodied fundamentally in our reproductive biology. Humans are really unusual. I mentioned that we are peculiar in our life cycles. We have probably the latest age at first reproduction of any mammal. It's very late. We've got high fertility, given how, we've got low fertility when you compare us to like a pig, right? We have singletons and we spread them out pretty well, whereas pigs will have a litter of 13 or piglets or whatever, right? But for our body size and for how late we begin reproducing, we are very fecund. We have a fertility rate that's about 50% higher than chimpanzees, for instance, in natural fertility populations. We have a super long reproductive span. You start reproducing at around age 20 or so, you end 45, 50. That's a long time to be reproducing for any mammal. And we've got extensive periods of overlap of dependence. And this is another picture from Brian Wood among the Hadza, this beautiful Hadza family with a mother with her 4 dependent children and her mother who allows her to keep these 4 beautiful children alive by subsidizing her foraging effort and her time and providing this babysitting. I think this picture embodies a lot of the peculiarities of the human life cycle. Among them include substantial post-reproductive lifespan, right, which is something that most animals don't have. So let's look at a little data. I've got a database of about 1,400 mammal species here, and I've just plotted things out as a function of body size. Biological things tend to scale with body size, and the modal mammal weighs about 50 grams, right? So there are lots of little things, there are fewer big things. That's one of those things that scales with body size. So you put these on double logarithmic axes, and the red points are primates, the black points are all other mammals, and the green are humans. And so we can see that for our body mass, we have a very late age at first reproduction. We have a very long lifespan. And we have low fertility, but we're not quite the same outlier that we are in age at first reproduction and lifespan. We're kind of in with all the other great apes in terms of our fertility. You don't really see how freakishly different we are, how weird we are, until you start to combine the parameters. And this is also a sort of engineering kind of idea. You have these different parameters, they have different units on them. Let's combine them and make some dimensionless numbers and try to get at the design features of the organism, okay? And this life history theorist, Rick Charnoff, showed that what I'm calling, it's the ratio of age at first reproduction to total reproductive lifespan, and I'm calling that relative lifespan, is constant across mammals, okay? And we can see I've got the 4 great apes here. For the 3 non-human great apes, we can see it's remarkably constant. The same thing is true for it's the product of age at first reproduction and annual fertility. I've called it reproductive power here. And it's a little more variable, but it's, constant enough for comparative biology, considering these things are measured with a lot of slop. How do humans fit in? So our relative lifespan is really right in the ballpark of the other great apes. What about our reproductive power? Ooh, 2, right? So way more than double what pretty much all the other mammals are. This is the thing that's really peculiar about humans. So we live a long time, but we actually also make a lot of babies, right? And those things typically don't go together. I suggested that a few years back that this pattern of very long life and very high reproductive power is consistent with a strategy known as bed hedging. Humans are bed hedgers. The long generation length that comes from a late age at first reproduction and a long reproductive span, coupled with relatively high fertility, means that you get to sample multiple environments. Think back to that plot of temperature over time, and zoom into a more local time scale. It's varying quite a bit, right? There's decadal scale variation that we know is going on in the Pleistocene in Africa. And if you had great information, right, you could say, I know that this is going to be a great year to reproduce, and you could pile all your reproduction into it, right? But if you're wrong, you're completely hosed, right? Because you've put all your eggs in one basket, right? Bed hedging is all about spreading out your risk, doing it a lot, and trying to sample a broad temporal series of environments. The essence of bed hedging is trading off the mean for a reduction in variance. And I should mention, the term comes from the racetrack betting strategy, where you bet at least a little money on every single horse in a race, right? And what that means is that you're guaranteed to lose money every race, but you're also guaranteed not to lose at all, right? Because some horse has to win. And you don't just lay it out at random. Presumably you have an idea about which horse is going to win, but you hedge yourself, right? And so hedging, of course, is diversification in general is right. It's the fundamental strategy for risk management. Okay, but why hedge bets, and why should humans in particular need to hedge? Why hedge? Humans inherited a legacy of slow reproduction from the great apes, right? We come from this great ape stock, and we have very low, in the broader scheme of things, reproductive capacity. So under the best of circumstances, a chimpanzee population is going to grow at about 1% annually, if everything comes together just perfectly. And the higher the growth rate, the less likely a population will go extinct. As humans moved into more variable savanna woodland environments, they experienced greater variance. And you can show, right, that your long-run expectation is essentially, it's a function of your mean, but it's also a function of your variance. Variance pushes you symmetrically around a mean, and when you have an absorbing boundary, right, that's a bad thing. You want to avoid getting pushed around that mean, right? So prolific reproduction is sort of the other way you do this. Like if you're a mussel or a sea urchin or something that lives in a highly variable, like coastal intertidal, right? What do? You just produce millions of gametes. That's not an option for humans, right? Because we inherit this legacy of the great apes. So we're trying to avoid extinction given these enormous constraints on our reproductive biology. And again, another photo that I think really encapsulates so many of these challenges that humans have and the embodiment of uncertainty in our life histories is this incredible portrait by Dorothea Lange, this iconic photograph of Oklahoma Dust Bowl refugees. And here's a mother in California with her infant son and her infant and her young school-age son. This is weird. We take it for granted because it's humans. You expect a young mother has a bunch of young kids. But it's really weird. A chimpanzee mother, birth intervals of about 5.5 years in Gombe National Park in Tanzania, another place where I've worked. She will wean her infant that starts that interval, right, at about age 4 or 5, and she will then never invest in that child again economically. She will never share food with that child again. She will never nurse that child again. Could you imagine doing that to this kid? Sorry, 5-year-old, we've got a new baby. You got to make it on your own, right? That's not an option for a human. Even those of you who haven't had kids probably know that, right? Sometimes you wonder with Stanford students, right? You have to explain that won't work, but I assume you guys know. So adaptation to uncertainty is embodied in our very reproductive biology. Given its central importance, it probably comes into our economic decision making as well. Now, I don't have much time left. I'm going to talk about two specific applications very quickly. So here is a schematic model, and I just put in the types of economic decisions I tend to think about as a reminder. We've got these 4 economic decisions, they're lotteries in the sense that they have variable payoffs, right? These are decisions that have variable payoffs, and we call them lotteries. And in the standard economic analysis, you have these different lotteries, and they get aggregated by a thing called utility, okay? The utility aggregates, it averages over these things, and you're trying to maximize that. And when people start thinking about, well, how do we mix economics and evolutionary biology? It's tempting to first simply substitute fitness for utility. But that's wrong for two reasons. First, no one but sociopaths thinks about maximizing their fitness. You know, you say, I must have more babies, and they, you know, and I must compete with, you know, people don't think that way. That's not something, and that's about, you know, sort of fitting into the observations again. But second, and more importantly, it would be a terrible control variable for your behavior, because fitness is measured at a time scale that's basically greater than a human lifespan, right? It's about your contribution to future generations. You can't sit there and have a real-time feed of your fitness, right? You need something more proximate to use. Fitness ends up being the arbiter of what things work and what things don't, but you want to have something proximate that you can use as a control variable, okay? To respond to adaptively to a changing environment. All right, so utility in the standard economic model aggregates over and averages over different lotteries. In our model that I've already shown you, right, the lotteries are still there. We've got these aggregators at approximate level. These are these sort of these proximate motivational systems, satiety, sexual satisfaction, love of your children, whatever they are. But what matters is that they are things that you can use to guide your decisions, right, over how you decide to mix your market basket, for example. And then fitness is the thing that aggregates over the top of this. This is a model, hierarchical model that Mike Price and I put together, and we've done a bunch of things with it. It turns out there are a system of equations that underlie this. We can put some constraints on there, and there's actually a whole talk where I talk about the constraints because it's sort of surprising and interesting where they come from. And we have results. Here are three very quickly. Distortion of decision weights, kind of like prospect theory. If the standard economic analysis, when you have a risky decision to make, is that you're trying to maximize the expected value of your utility. And think about what expected value means. It means that you have a linear combination of some weights, they happen to be probabilities, but they're decision weights, and some outcomes, right? It's a linear combination. It looks like people aren't putting together linear combinations of weights and outcomes, okay? They're using some sort of weird curvilinear thing that Kahneman and Tversky have suggested looks kind of like that. When we use fitness as a criterion, as an objective function, right, what we get is decision weights that curve like that. Okay, so that was cool. Another thing is high risk aversion among the poorest people. There's this idea, it's kind of this folklore, I think, that poor people have nothing to lose somehow. You know, in the sense that they're very resource poor, and so they should be willing, they're natural entrepreneurs, right? They should be willing to take risks because what have they got to lose? Well, what they have to lose, when you think of us as biological entities, is they have everything to lose, right? They're poor. And so if their financial decisions, if their economic decisions have an impact on their survivability, then we should expect them to be actually risk averse. And in this framework, it turns out that they're extremely risk averse, okay? And then finally, we can recover without any sort of active choice what look like preference reversals, some of the classic paradoxes of choice that came about in the 1950s. That's a little more technical, but it's a cool result too. Just want to remind you, as I get to my last point here, about the diversity of habitats that humans live in, right? We come out onto the savannah. We can live in these mixed rainforest agricultural lands, as in Uganda again. We live in the tundra, right, inside the Arctic Circle. Here's some Venezuelan llanos, home of swamps and big snakes, right? This is where anacondas live. They're very successful hunter-gatherers who live there. We live on the coastal shore as fisher folk. We live on temperate prairies, right? We have a wide variety of habitats, and presumably our sort of choice calculus should be a little different depending on where we're actually making our decisions. So as generalists with tremendous capacity to learn, it seems reasonable to suppose that the human capacity to make rational decisions has an ontogeny, right? Meaning it has a development. You have to learn a little bit about it, okay? And I've developed a simple model of learning about one's uncertain environment that helps understand one of the most vexing results in this irrationality literature, which is inconsistent time preferences, right? The fact that we value like waiting a day differently, whether it's today or whether it's next year, right? We care a lot about waiting from today till tomorrow, but we don't care that much at all. You know, a year and a day from now, whatever. It's a year from now. This drives economists crazy, right? It may seem common sense to people. I think that that's an interesting insight, but it does drive economists crazy. It's one of the fundamental anomalies. So I have this simple model that has basically 4 parts. The first is that your time preferences. Why do we care about the present more than the future? Well, a reasonable way to think about that is because there's the chance that you might die before you recover a reward that you delay. Or less dramatically, that reward might go away, right? Your friend might forget, or it might be a resource that gets swooped on, right? So there's a hazard of failure of this resource. And you can then have a time-consistent prior, which is like an exponential distribution, right? That you value all delays of the same amount by the same amount. That's your prior distribution, right? Consistent with the prior. You can then go out and learn about the environment. But a lot of these important economic decisions, things about like how what you plant this year yields your yield, 9 months from now, a year from now. You don't have a lot of opportunities as a kid to learn about that. You have a few. So you're probably at best going to learn about it with uncertainty. When you integrate the uncertainty of it, so the posterior looks pretty good here, right? I figure again I'm on fairly safe ground, Google, Bayes, right? Your posterior looks pretty good, but in fact, when you integrate it to give your posterior predictive distribution, all of a sudden, you've got all that uncertainty that causes this big plateau here. And it essentially turns into what's known as hyperbolic discounting, right? So it's an inconsistency in time preference, because you've got this fat tail that you have to integrate over. So uncertainty and discount rate leads to inconsistent time preferences. There's the exponential prediction, right? The discount rate with no uncertainty is exponential. You add uncertainty, and what you get is essentially this hyperbolic function. I was really excited when I read it, because it's a really simple model, right? It's just a simple little Bayesian model. I was like, wow, I've really nailed it this time. Turns out, then I then went back to the literature. It turns out a bunch of people have said it, which is always a bittersweet moment. On the one hand, you're like, damn, I thought it was so original. But on the other hand, it means that I had the same good idea that Partha Dasgupta had, and that's always a good thing, right? So, you win some, you lose some. So I'm going to give you 3 takeaways. Maximizing fitness distorts economic choices, right? We've seen this repeatedly. But it maximizes fitness, right? And that's the direction that selection is going to push the population. Uncertainty changes optimality predictions qualitatively. When you put uncertainty into the game, you get different answers. And that evolutionary theory has promise for providing a comprehensive theory of choice. It's very much a work in progress. I'm excited about the potential here. I'm excited about trying to recruit some more people to work on this. And I'm going to thank you for your time, and I'm happy to entertain. Yeah.
Hello. So I have basically a question about the role of like social signaling and economic decisions. I'm thinking particularly there's that game economists like to point to as irrational, where 2 people can split a pile of money. One makes an offer, the other accepts or rejects.
Yep.
Typically, if it's asymmetric, second one will reject, and no one wins anything.
Yeah.
Which to me it seems like that's because like in a tribal environment, you're trying to teach other people, don't try to make
Costly punishment, absolutely, yeah. I mean, so this is another area that has actually gotten a lot more attention, I think, from evolutionary anthropologists and evolutionary biologists is what's sometimes called our prosociality, right? This intense sociality that we have that's reflected in these food sharing networks, right? But that we have this psychology of we don't like unfairness, right? And when you play the dictator game, right, you punish people who don't give what you perceive to be fair offers. And presumably this relates to this need for ensuring cooperation in small-scale societies and punishing cheaters. Yeah, thanks for that.
Yeah, quick question, or maybe a related question. So if we're really concerned about comfort and survival and things like that, it's amazing that humans will migrate to some of the most uncomfortable places.
Yeah.
And will willingly venture out. Like, why would a rational creature go to the South Pole, go to the moon, go to Mars?
Yeah.
They're dangerous. They're not very pleasant. But
Well,
do we as creatures we tend to be rather curious?
Yeah.
Does that make us somewhat different from other animals?
I think that anything that makes its living as a generalist is going to be curious. I mean, lots of primates are super curious, right? I mean, if you live around here and you have like French doors, you've possibly seen raccoons at your door, just sort of like looking in, like, hey, what's going on in there, right? So I don't know if curiosity. We certainly, I think, take curiosity to another level. All of those things. If you go to Mars and you come back, that's a pretty high status thing to do, right? You have a social signaling going on, right? If you come back, no, right? And if you think about my Bayesian model, right? How many opportunities do you have to learn about what the actual hazard is? Suppose you have like a really flat prior. You've never seen anyone go to Mars, so it could be anything, right? So I think that sort of explains some of the unusual sort of decisions that people seem to make. Moving into the Arctic to live, right? It may seem uncomfortable to us, but if you're Inuit, you do pretty well in general, right? And there's a living to be made there, and people are incredibly adaptable.
Question. Thanks for the talk. Do you see any other species that have environment that are evolved in uncertain environments that share a similar pattern in reproductive power or other characteristics?
Yeah, that's a great question. I don't really know. So the classic bed hedgers they're a bunch of birds, like, again, local environment, red-tailed hawks, right? So a lot of the raptors will do this thing that's really kind of perplexing at face value. They'll lay clutches of 2 eggs, but only one will ever fledge, right? And it seems incredibly wasteful, right? And it's a classic bed hedging thing. If that first one fails, then the second one is there, right? And the cost, you're paying a little bit of your mean, you're paying out a little insurance policy, right, to insure against catastrophic failure. So there are lots of birds that engage in this type of bed hedging. Reproductive power, as I've called it, I've not seen it in any mammal. It's possible it exists in other, but the way the Charnoff model works, for this model you have to be a mammal. Like, you could come up with these sort of dimensionless design features of different life histories, but it only works for if you have the same kind of general reproductive biology. Yeah.
So in light of your research, maybe academically you wouldn't make any recommendations like this, but personally, do you have recommendations on how to motivate people psychologically and collectively to address issues like climate change that we're feeling in the present now, but we'll be feeling a lot more in the future?
Well, I have pretty strong opinions about the way we value the future, and I think that it seems like it's a bit of a moral argument, but when we say we want to take some steps to mitigate climate change now, whenever we do a cost-benefit analysis, what's going to happen is that you're going to take a discount rate, right, of the value of an investment today, a couple of hundred years in the future. And that's the real rub. It's both the fact that you're valuing the present more than the future, but you're also, all these things play out at very long time scales. So you throw in a 4% discount rate, and it's very difficult to come up with a cost-benefit analysis that favors mitigation now with a 4% discount rate that pays out its benefits in 200 years. So I think, and I'm not alone in this, there are a bunch of environmental economists who are engaged in a very vigorous debate on this, that we should use much lower discount rates for thinking about cost-benefit analysis with these long payoffs. Martin Weitzman at Harvard has suggested using the absolute lowest discount rate that you can imagine that makes it tenable because of this problem, right? And because the tail risk of these outcomes are so huge, right? So that's something I take away from this, don't overvalue the present. But it's easy for me to do that. I live in Palo Alto, right? We all live in pretty predictable environments, right? We're quite privileged people, and it's easy to say, well, we should really value the future. And this is some of the work that my colleagues who I showed you briefly have done, showing that, if you're poor, so they're the classic marshmallow experiments that were done here at Stanford, right? And, give a kid a marshmallow and walk away. Say, don't eat that, all right? Because if you do, that's all you're getting. But if it's still there when I come back, you get 2, right? You walk away. And it turns out that, these kids who struggle they're looking at this marshmallow and they're like, oh God, I want to eat the marshmallow so bad, right? It turns out that it correlates very well, that your ability to put off that reward and get the larger reward after a little delay predicts a lot of things about your success in life. It's really hard, anthropologists have found it really hard to go into places and replicate these types of economic games that we play all the time, including the dictator games and these things that we talked about before. In part because people are like, how do I know you're going to be back with your 2 marshmallows that you talk about? I'm going to take that one right now, thank you very much, right? And so that's just a cautionary tale that it's easy for me to say we should value the future more because, I have a pretty low discount rate because, I live in Palo Alto. As a society, I think we should be modeling the future, valuing the future more than we do. That's a really long answer to a pretty straightforward question. Yeah, okay. Yeah?
How does our evolutionary history play out when we are not 200 people in a small bag, but we are 7 billion people?
Yeah.
Play out in terms of the societal structures that we construct.
Yeah, it's really, that's a vexing problem, right? That we sort of develop these in-group and out-group identities, and that they probably are very functional when you live in a band-like society because your in-group is really your everything, right? It's maybe not so functional when you make the rest of the world your out-group, right? And the same sort of rules of morality don't apply to them and that sort of thing. That's a real problem, and solving that, there's a prize for someone, right? Is if we can figure out how to really begin to address that. Equally importantly, in the world we live in, when you're a peasant farmer and you plant yams and some maize and whatever, you sort of you place your bet and then you tend it and you hopefully get a big payoff, right? There's a direct causal interpretation of what you do and what you get. In the world we live in, we have all this complexity, and we don't necessarily pay the cost for bad decisions right away. And I think that makes it very hard to learn about good decision making, right? And so there are a number of people who've developed sort of the curricula for teaching kids how to make risky decisions. I think that giving kids some responsibility and getting them some skin in the game is a really important thing. So that's a little off of your question, but I think that that's another real challenge to thinking about how our brains were designed to make decisions and the types of environments in which we have to do it now, many of us. Yeah.
If we predict greatly increased variability in the near future, what would you predict with those functions, e.g. More longevity or things like that in us?
Well, first of all, we have to get through this possible bottleneck, right? And I say that flippantly because otherwise I'd just descend into depression, right? Sure, it's conceivable that there could be more selection on even more spread out reproduction. I mean, the thing is that a really interesting observation that we make in development economics and demography is that as soon as you can ensure the more or less certain survival of your kids to reproductive age, people voluntarily reduce their fertility, right? And so we had this model called the demographic transition model, and it predicted the sort of time scale over which this happened, and it seemed to explain the historical data very well. And then, late in the 20th century, these places, like a lot of places in the Middle East and North Africa, and in Asia, in the tiger economies, like fertility fell like that as soon as kids could be counted on to survive. And so, yeah, if our sort of technological and social technologies can keep up with ensuring the child survivorship, right, and keeping keeping it favoring economic investment, then that sort of relaxes the selection pressure to spread everything out for sure. And I think that should be a goal that we have, right? If we want to avoid sort of negative population consequences, make sure that kids survive to adulthood, right? Because that changes everything about people's investments. And that's really what this, given that you can't affect that, right? As a hominin, a million years ago, right? You don't have the technology to really mitigate that, right? So what you do is you spread everything out. But if we have the chance to actually solve it, right, then that's the better solution probably. And that also sort of reduces the selective pressure, I think. Yeah. Yeah, thanks. Thanks a lot. It's fun.